Hambini fans, and welcome. Today I'm going to do a case study. This is, I guess, typical of some of the things that I get asked to do. A lot of people come to my videos, click on the website and send me an email along the lines of, "Dear Hambini, I've got a creaking bottom bracket, or I've got some problem with my bottom bracket, can you help me fix it?" So today, what we're going to do is I'm going to run you through the method of manufacture for a BB86 unit. So a customer had a problem with a BB86 unit, and this is from start to finish and some of the engineering that goes on behind it. I will warn you in advance, the engineering in here does get quite heavy, but a lot of people have asked for it, so I want to give the people what they want. So let's begin. What I've done is I have created a PowerPoint presentation. It's only really there as a bit of a help guide, but I'll be flinging my arms about and probably using the orange board behind me to talk you through some of the features. But first thing first, let me explain what happened. This customer had a Scott Addict. It's a BB86 bottom bracket, and he lived in the USA. And he had looked at the standard Hambini bottom bracket, and what he'd noticed was, if you can look in this picture here, a standard Hambini bottom bracket, which is one of these. Well, this is a racing specification BB86, so this has only just come out, but it's very, very similar geometry on the exterior. That wouldn't actually push through his hole because he had like a cable guide that did his front mech and his rear mech, and that impinged into the hole. So we had to do something about that, and if I click there, you can see this cable guide obstruction. Right, so just as an overview, what I'm going to show you is this is a cross section of a BB86 bottom bracket. So it's 41 millimeters. So on this, that dimension there is 41 millimeters, and it's 86.5 millimeters from here to here. There is a flange on here just to locate it, but this is what you would have in your bike frame. So that obstruction would not really be shown on just a standard Shimano specification drawing. Shimano usually rate their engineering highly, but what they've done here is they have made a decision purely for commercial reasons. So they've made the hole 41 millimeters. By doing that, they preclude all the 30 millimeter cranksets from installation in an easy way. You can install a 30 millimeter crankset in a BB86 bottom bracket, but you will have to do some modifications that I certainly wouldn't recommend. A 6806 bearing, which is 42 millimeters, won't actually go in that hole, and that's why they made it 41, so they could get rid of that lot. So this is where the cable obstruction is. So we've just taken a cut through the bottom bracket, and that's where it is. What was gold dust is what this customer provided to me, and it's really nice to work with people that I guess have an understanding of some of the technical details that you have to go through as an engineer. This customer provided to me dimensions for his bottom bracket shell. So he had the outside, inside at 3 o'clock to at 9 o'clock to 3 o'clock and 6 o'clock to 12 o'clock position. So we're around the clock face, the cross. So between there and there and there and there, he provided those dimensions to me. And the Scott one is actually a bit tight. The other problem was it was quite significantly tapered. I guess the limiting factor in all of this was his desire, his necessity, to be able to get his cable guide there and not have to machine it or take it out or do some heavy modification. So he wanted all of that in the bottom bracket. What that meant was that the center section of the bottom bracket, this bit here, had to be necked, and we'll come on to this now. So his specification was he wanted a creak-free bottom bracket, he wanted exceptional bearing life, NTN bearings because that's what he'd seen or used in the past, and an interface to Shimano Holotech cranks. When you get to this stage, what you have to do as an engineer is you have to talk to yourself, that's probably the wrong expression, but consider what options are available. So you could go for a split conventional bottom bracket. So a conventional split bottom bracket is something like this. So we have three pieces. So we have one that goes in one side, one that goes in the other, and a center sleeve in the middle. The problem with this is, you know, I can move that. There is no real strength in the bottom bracket. You are completely reliant on the bicycle frame and all of that. If there's any misalignment, this will not fix it. And if you have misalignment, you could get creak, but more than likely you'll get really quite poor bearing life. So you know that's not really great. The major advantage is it's very, very easy to overcome that obstruction, because all you do is put the put one side in, push the sleeve in over the obstruction, and then push the other side in. So you know that's straightforward. They're also very, very easy to make. This is considerably easier to make than this. Now I've almost created a rod for my own back with these things, because I only machine from one side. So when you put this in the lathe to machine it, if my finger is the cutter, it comes along, does that, machines all of that, and it machines these things also in one go. It that's the way I do it, because it's more accurate. Another aspect in all of this is dealing with thin wall metal structures. Thin wall metal structures are not easy to machine, because when you come along with your cutter tip and then you go near the metal, what happens is the metal deflects. It's almost like trying to scrape rubber from a rubber balloon that's been inflated. As you push your cutter in, the material deflects. As you go away, you think you've machined a millimetre off, and you'll find you haven't. So that's why I never CNC anything that's very, very thin wall metal. The other things associated with this are you've got a stiffness advantage. The stiffness advantage, when I made these things, I didn't make them this way to make them stiff so that people would feel the pedalling advantage of having a stiff bottom bracket. Obviously that is advantageous, but the real reason is because when you are under load, you will actually deflect your crank. So the crank will deflect, it will bend ever so slightly, and that will place a load onto your bike frame. Bike frames are not that stiff. They're almost like jelly in comparison to the crank. So the crank's significantly stiffer. If the crank's bending, you might induce a fatigue failure, but you will almost certainly cause premature wear, well, just accelerated wear, not necessarily premature wear, in the bearings. So having a stiff metal structure around will reduce that effect. So if we come on to the next slide, on the left hand side we have the special model. On the right hand side we have the Hambini standard one. So you can see, then this is a cut through. So you can see that it probably just looks to the naked eye that I've just brought these sections in, but there's a bit more to it than that. There are some subtle differences which I will point out now. Firstly, where the thing is necked, there is a stress razor. And what a stress razor is an area which is exposed to it's more likely that something will fracture there. So as an example, if I took a piece of paper and folded it here, that fold is a stress razor, because if I tear, naturally the tear will want to go along the point of least resistance, and it's the same in a bottom bracket. So that stress razor is that corner joint. I'm going to come on to that in a second. Another thing is the necking. So because it's actually thinner, you reduce the stiffness of the bottom bracket. Now, I don't make these things wide to be awkward. They are that width or that diameter, because one of the disadvantages with a Hambini bottom bracket, and it's an inherent disadvantage, is they will be heavier. So they're on average about 30 grams heavier than in this case, a Shimano standard nylon bottom bracket. To reduce that, I make the walls very, very thin, but I rely on something called second moment of area. And what second moment of area is an object's resistance to bending or crushing stresses. Making it wider increases that value, the second moment of area, and again I'm going to show you on that board what that's all about. And then some of the subtle things associated with the mechanics of these things. This small area here, which I've highlighted and called abutment, is where the bearing presses against. A lot of bottom bracket manufacturers, let me find one, here's a rotor bottom bracket, so I've got one of their bottom brackets. Fine Spanish engineering, utter crap if you ask me. I'm not supposed to slag off any other manufacturers, but utter rubbish. This is a rotor bottom bracket, and oh well, let me get the bearing from the rotor bottom bracket. So this is the bottom bracket, there's the other end of it. It's a B-Bright model. A customer actually sent me this. Let's just show you what happens. The bearing just comes straight out. There's no abutment on there. The abutment is there to stop the bearing. The bearing will distort. It doesn't have infinite friction. Infinite stiffness. So when you're in the on the bike and you put load through it, now people will talk in watts, but really I'm thinking torque. As you put high amounts of torque through it, the bearing will flex ever so slightly. As it flexes, the black seal will touch the metal if you do not have an abutment. So that's one of the things I've got on there. That, it might just seem like it's a 0.5 millimeter of metal, but it is an absolute pain in the backside to be able to machine that in one go. The next part of this video, I'm going to talk about the design and the manufacture of this bottom bracket. So I've already picked a necked BB86 bottom bracket, and that's what I'm going to do. Just to talk about some of the background of this, a lot of people ask about bottom bracket stiffness, so I've done a graph to illustrate this. And if you start off with, I haven't picked an especially flash frame, but a Hong Fu frame with a BB30 bottom bracket. If you just put the bearings in with the snap rings, you've got, and this is a bit tricky because there is no uniform method of measuring bottom bracket stiffness, so you need to take this as a relative. Just a standard Hong Fu frame has 103 newtons per degree of bottom bracket stiffness. If you put the wheels manufacturing ring converters in, so these black Delrin adapter type things, they actually drop your stiffness down, and that's because the bearing is in an offset position. So you've got the bearing here, and then you put that piece into it. The load is transmitted through here, across and up into the bearing. You really want the load to be between the bearing surface, so you actually lose a bit of stiffness, and it's about 15%. So it's a number that you'll be able to feel. If you went for the Praxis converter bottom bracket, so these are they're made out of steel and they thread in, and what happens is the metal splays outwards. You would increase your stiffness to 135, there or thereabouts. It's not an exact number. That is because, one, it's made of steel, so it's a lot stronger than plastic or the frame material of the bike. So if it was a carbon bike, the steel's loads stronger. And then we come on to BB Infinite. So BB Infinite is a one-piece bottom bracket. Their bottom bracket is around 390, so instantly you've gained 3 times. And then you see my two bottom brackets, Hambini Classic and Hambini Racing. So the Classic one is a slightly different material and a slightly different geometry than the racing ones. The racing ones either come in black or orange. So this one is a racing model. and this one is a standard model, so that's just pure aluminium. The reason why these are stiffer, even the standard one, than the BB Infinite is the guys who ever made BB Infinite, they made a conscious decision to in their bearing placement, they don't have full retention on the bearings. So if I explain what that means, if we've got this bottom bracket, the bearing sits completely in the bottom bracket. There's metal all the way around it. This is the BB Infinite bottom bracket, and the reason why it's essentially not as stiff as a Hambini bottom bracket is to do with the bearing retention. On a BB Infinite bottom bracket, the bearing is not fully retained, so the bearings are 7mm thick, and only about 5.5mm is restrained. There's 1.5 millimeters that's just open in free air, and the reason they do that is because they have these plastic cups that go into their bottom brackets. Their ones are moulded rather than machined like the ones that I use. It's a design difference. In reality, will it make a big difference? No, the stiffness values are so high that it's almost arbitrary. What you're looking at here is a 3D model of the bottom bracket body, and this is an exact copy of what was produced. What we can do is we can take a cut through there, and that's the section of it. So we've got a flange on this side where it locates, and these two landings either side. It's pretty obvious now where this stress razor is. It's going to be there, and I just know that from experience, but I don't really like to rest on my laurels. So what I did was I went and did some loading studies. Now these loading studies, I will tell you now, the values you're about to see on the screen I've completely fiddled, and they're fiddled so that no one copies them, but you'll get an idea of what it's all about. So if we click on show, what I did was I fixed one end and loaded the other end. So the fixed end is the flanged end, and I loaded the other end with the effective weight of a car. And you're probably wondering, well, why does he put the effective weight of the car? And the reason is because of fatigue loading. Every time you pedal, you are putting your right foot down, then your left foot down, right foot down, left foot down. You're creating a cyclical stress, and this SolidWorks system will demonstrate a cyclical stress. So when it's blue, that's unloaded. As it starts to go red, that's loaded. And the red areas are where you are going to get the highest stress. So unsurprisingly, it's very close to where I put the stress razor in. That's one aspect of it. And if I did the same thing for a standard Hambini bottom bracket, the standard one is slightly stiffer. One thing the customer asked for is he wanted titanium. He didn't want to mess around, so it was made out of titanium. The geometry of the bottom bracket changed ever so slightly to accommodate the ability to machine titanium, but you can see the way the thing is loaded. Another aspect of all of this is the displacement. So displacement is, as I apply the load, how much does it deflect and where does it deflect? Now, if you were to just apply load on one side, so you fix the flange side and apply load on the other, the very end of the bottom bracket deflects the most, and that's what you would expect. And that's one of the reasons why I put full retention on the bearings, because I know I'm going to get maximum deflection there. Which is more important, dust seals versus fully restrained bearings? In my opinion, the restrained bearings. In other people's opinion, well, the dust seals, and they've got enough retention. But there you go. The other thing that I've got is I've got a different loading case where I've sectioned it, so we can see what the loading is through the middle of the bottom bracket. So where that abutment is, the abutments here, that causes a slight stress raiser, but is nothing compared to the actual neck. So that's why I don't neck it, because it's not ideal. Sometimes you can't avoid it, but it's not ideal. So before people had finite element analysis programs, what they used to do was use hand calculations. And I alluded to this earlier about second moment of area. Second moment of area is the ability of an object to resist bending. There isn't really a better example than a ruler. Now, a ruler this way is fairly flexible. Okay, that's a metal ruler, probably a poor example, but you can bend it. If you turn the ruler that way and try and bend it, I've got no chance. And that's because the second moment of area in that direction, which typically as an engineer you would probably call the Y direction or the Z direction, is much more than the X direction. The actual coordinate system will vary, pick what you want. Second moment of area is, the formula is the integral of y squared dA. And I don't really want to make the maths all that heavy, so I won't. But if you integrate all that out, and you'll get an answer. The absolute, finite number for a circular section is the outer radius minus the inner radius, both of them raised to the power of 4, multiplied by pi divided by 4 gives you the second moment of area. So second moment of area is measured in meters to the power of 4 or inches to the power of 4. Because we're working with thin wall sections and fairly small numbers, you can do an approximation, and the approximation is pi r cubed times t. So if I take a 30mm axle, or which would be a BB30 axle, it would be pi times 15 times 10 to the minus 3 because it's in millimeters, all cubed times the thickness. So the thickness might be a millimeter, and that will give you an answer. What that means in real terms is, if you forget the maths, if you go from a 24mm axle to a 30mm axle, you will increase the stiffness of the crank by almost double. So you'll almost double it. It's actually 1.95 times more. So that is the second moment of area. So to give you a graphic example of these bottom brackets and the second moment of area, what I've done is I've got a severely necked bottom bracket. Then that tips the scale at 165-ish grams. Then the next one is a bit of a halfway house, 146 grams. And then we've got the final one, which is a racing model, and that one is 125 grams, but it's the least necked. So to explain a bit further about the design process, the next thing that has to be considered is the Young's modulus of the bottom bracket material. Most of my bottom brackets, the standard ones, are all made of aluminium. The racing ones are made of a different type of material, and the one the customer asked for was out of titanium. Now all of these things have what's known as a Young's modulus, and a Young's modulus is the ability of a material to resist stretching. So rubber has a very, very low Young's modulus, so you only have to apply a small amount of force and it stretches a long way. This is a typical kind of graph that you would see for Young's modulus. So stress, which is sigma, is measured in newtons per meter squared. You might think, well, what does that mean? Well, you actually use it all the time. When you pump your tyres up to 11 bar, 1 bar is 100,000 newtons per meter squared. They just call it a bar because it's an easy number. If you're in the US, PSI or KSI, which is kips per square inch, is a common unit. This eta, I think it's eta, I'm not quite sure, I can never remember, is the strain. And what strain is the extension divided by the original length. So it's not measured in any units, it just has a number. If you were to draw the lines out for each of these, you would get something like this. So So all three lines are supposed to be straight, but that represents aluminium. That is titanium, and that will be steel. So I'm going to call that Fe for steel. It's actually iron. Aluminium, you don't have to apply that much force to it to make it move. At the other end of the spectrum, steel, so what Praxis make their bottom brackets out of, is very, very stiff. You're obviously paying a weight penalty. In between is titanium. Now, titanium is probably the ultimate material for a bottom bracket. It's got a very good strength to weight ratio, and it has a decent Young's modulus. So that Young's modulus makes a difference, because you can make the walls thinner, and if you can make the walls thinner, you can make your bottom bracket lighter. Titanium is slightly heavier than aluminium, so there is a design consideration to go in with that. The problem, or one of the issues associated with a BB86 bottom bracket, is what's known as a tolerance stack-up. What this tolerance stack-up means in realistic terms is it actually causes a bit of a headache, and it's one of the reasons, primary reasons, why bottom brackets creak. You've got press fit bearings that go into this bottom bracket, which goes into the bike frame. The press fit bearings have an interference fit, and so does the body of the bottom bracket, and they're all an interference, usually around M7. When you change the material, you have to change the level of interference that you get. So aluminium has a particular level of interference. It might be 10 microns, it might be 20 microns. Titanium has another level, and it's less than aluminium, and the reason is because titanium has a higher Young's modulus, so you don't need to have as big an interference to get the same level of retention. I suppose the extreme end of this is plastic. So this is a Delrin bottom bracket, and the Delrin bottom bracket, that has the same interference as this, but I wouldn't be able to do that on this racing bottom bracket. There's no way I could do it. But with a Delrin bottom bracket, same press fit level, you can just push it in and out, and that's the issue with a tolerance stack up. So obviously there's quite a lot of things involved in making a bottom bracket, and the final bit of all of this was, I guess, manufacturing it. Manufacturing these types of bottom brackets is technically difficult, and the reason it's technically difficult is if you want to have very good bearing alignment, you can only machine this from one side. If you take this out of the lathe, turn it over, and then machine the other side, machine the other hole, you're almost guaranteed to be out. Thin walls, you need to have thin walls, because otherwise you make the bottom brackets heavy. With the thin walls, and if this pen represents the cutter, as you push in, it's deflecting the material. The combination of all of these makes it technically difficult. So I'm not going to go into the actual way these things are held, but that is one of the differences between, I guess, my bottom brackets and everybody else's, because I only machine from one side, irrespective of what material it is. So fast forward 2 weeks, customer receives the bottom bracket and he installs it on his bike, and he sends me an email. He said, "Dear Hambini, I installed it and have done a few rides already. Channeling the dark install now for cuss words of positive emphasis, not so much as the slightest effing creak coming from the bottom bracket now. It was tight as F word going in, and the bearings are smooth as F word. Effing beautiful. I'm going to ride it for a while, then give a glowing review." And he did. He did put a review on my website, so thank you very much to that individual. So yeah, that is a case study of how the bottom bracket was fixed. Okay, it was an expensive bottom bracket, but you can see some of the pain in the rear end. I won't say pain in the rear end, because I really enjoyed it. I do enjoy these sorts of projects, because the kind of things that I work on normally take ages to come into fruition, and I'm not completely responsible for everything. You do have to have other people doing things for you, but in this respect, this bottom bracket was, completely made by me, and so it's a very rewarding thing to have. So that's the end of this case study. There will be more. If you want a bottom bracket doing for yourself, send me an email and I will have a look at it for you. And that's it. So until next time, thanks very much.